Hi, everybody. In a moment, you're going to enter the data show. Welcome to the data show. I'm Chris Greco. For the next 30 minutes, we'll be talking about different parts of data, how it works, how to research it, how to get data, how to analyze it, all the different things that have to go along with that. What we're going to center on today is something that I covered a little bit last week, and that was medical diagnostic data. How it works, what it does, the different statistical formulas go along with that, all these different things. So what I want to talk to you today was about the cholesterol formula. Now, many of you may not realize that the cholesterol that you get, whether it be the high density lipoproteins, the low density lipoproteins, triglycerides, all those are done by what they call assay. They take a look at it and basically they measure it, that type of thing, measure cholesterol. But there's ways of formulating to get like the LDL or to get the HDL if you have the other three, just like any other equation that you would think of. So what I want to do is just talk to you, what we're going to do is just take a look at these things separately and then talk about how this formula has been generated basically for decades. Well, I shouldn't say that. A half a century. This formula that I'm about to give you is called the Friedewald formula. And the Friedewald formula, let me put that down just so you know what it's called. It's called the Friedewald. I think it's Friedewald. I think it's Friedewald formula. Anyways, so it's the Friedewald formula, and this thing has been around since 1972. 1972, folks. It's a half a century year old. That's the things that the way that this thing has been going. So let's take a look at this just for a second. So let's say that you have an HDL, and this HDL is going to be, I don't know, let's say it's let's pick a good HDL, so 60, right? And your LDL is not going to be all that great. It's going to be about 200, right? And your triglycerides, that's a separate measure, triglycerides over 5. So basically what has to happen is you have to take the triglycerides and then divide that by 5, right? So let's call the triglycerides, let's say they're 100 divided by 5. Okay, so 20. So what's the total cholesterol? That equals the HDL plus the LDL plus the triglycerides over 5, right? So it's going to be 280 is going to be your area, right? So that's what that's going to be. So now let's take a look and say, all right, let's say that your HDL is 50. Your LDL has lowered now down to, I don't know, let's say it's 150. Okay. Your triglycerides over 5, triglycerides kind of raised, so it's going to be, I don't know, let's say it's going to be 300. So it's going to be 300 over 5. So you've lowered your LDL by 10. You've lowered you lowered your LDL by 50. You've lowered your HDL by 10. Your triglycerides have increased, and because of that, your total triglycerides is not that different. It's not that different. So let's reverse these. Let's say let's say that I have an LDL of 50, or an HDL of 50. I have an LDL of 100. My triglycerides, we're gonna bring them back down again. We're gonna say, let's bring them way down. So we're gonna say 80. 80 divided by 5. So 80 divided by 5, and we're going to have, what are we going to have total here? Is going to be 166. So let's say you really, really work hard at HDL and LDL. You go out, you exercise, you do all kind of crazy crud just to get this thing going, and you end up with a HDL of 50 or of 100, an LDL of 50, but the triglycerides you just couldn't get them any better. So you're going to still have the 80, right? 80 divided by 5. So your total cholesterol is still 166. In other words, people can sit back and they go, I have 166. I have a good cholesterol. I have 166 and I have a bad cholesterol. So I mean, because the LDL is 100, right? Right on that edge of being bad, right? But your HDL is kind of down. It's not all that great. So in other words, you can see where this formula has some issues. And the idea behind this was the triglycerides. See, the triglycerides over 5 was trying to estimate what they call the very low density, VLDL, the very low density lipoproteins. Well, they found out through some studying, through some other things, that this is just not the way that this works. The VLDL is not a good estimate of triglycerides over 5, especially if the triglycerides are very high. Then what happens is that estimation goes away. Now, why wasn't this corrected in the 1980s or whatever else? It's because the formula was working. It was doing fine. There wasn't any problems with it, so to speak. So they really didn't have they didn't try to fix it. They didn't try to do anything to try to fix it. They didn't try to do anything. Well, along comes the American Council of Cardiology. Right now, here's something from 2020, and it says new information on accuracy of LDLC estimation. So why did they say LDLC estimation? I don't understand this. I'm going to say okay to the cookies. So because I can reverse this whole thing. I can reverse this. I can say, okay, let's say my total cholesterol is 203. All right, and my triglycerides, let's say again, are 80. Are 80, right? 80 divided by 16, that's 5. And then your LDL is going to be, let's say it's going to be 80. So from that, can I determine what my HDL is going to be? Oh, I'm sorry, my HDL is, let's say my HDL is 60. Can I determine what my LDL is going to be? I don't know what it is. Sure, I can say that equals to the HDL, right? So it's going to be it's going to be total cholesterol minus the HDL minus the triglycerides. So my LDL is 148. That's not good. That's not a good number. 148 is not a good. Again, this Friedewald formula, right? So you can determine the LDL if you have the HDL, the triglycerides over 5, which is supposed to estimate the VLDL, and the total cholesterol. So what does this all tell us? Well, it tells us something very important, and that is that no matter what you do, you have to take a look at the different formulas to find out exactly what's going on. So getting back to the new information. So new information on LDLC estimation. So it goes into different aspects and what was going on, and developed in 1972, estimates LDLC as total cholesterol minus HDL minus triglycerides over 5. So with the latter term, as I said, estimating the very low density lipoprotein cholesterol, whatever they always say LDLC, HDLC, all this stuff. So originally developed for research from a sample of just, notice they say just 448 individuals. We have gone over this before, we've gone over it before, and we've gone over it before. If the sampling is not good, then we have an issue when it comes down to anything else. And this, again, this can be done by just taking a look and saying, okay, we'll do a new one here, a new area. And then what we're going to talk about is we're going to talk about the add-ins. So we're going to go to the add-ins and real statistics. And when we do the data analysis tools, we sit back and we say, okay, go to miscellaneous, and then we have statistical power. So I'm going to sit back and I'm going to say, okay, look, if I have a one sample normal and I want to know what the power is going to be, right? So the effect size, if the effect size is 0.2, which is actually a pretty good effect size, and my sample size is 448, which it was, then what do I have? Well, my power is going to be 0.988, given the effect size is 0.2. If my effect size is 0.4, then all of a sudden it kicks up. So what happens is when you have an effect size of 0.1, which is that's pretty high, but it does take into consideration the type 2 uh, the type 2 error that you get. Then all of a sudden you have an issue here. So let's say I have that effect size is 2, but my tails are only 1. Then what happens? Well, it kicks up again. So the power is really good on this, even though the sample size is 448. So the effect size will really, I mean, if you have an effect size, like I said, of 0.3, all of a sudden that kicks up to 0.99. Your power is very high. So even though they said that it's just 448, the statistical power is good if the sampling is representative and if the sampling is random. So those are the things that have to go along with that. If you don't have a random sampling and you don't have a representative sampling, then all of a sudden that can, no matter how good the statistical power is, it still doesn't help with the overall unbiased sampling that you want to have. So it's, this is what happened here, and then it talks about different aspects. So what they want to do is they wanted to make in 2013 they did a paper, and they decided that, hey, look, there's a problem when you're estimating LDLC when the triglycerides were less than 400. 400 is pretty high triglyceride, folks. I mean, but the fixed factor of 5 is instead replaced by an adjustable factor on a patient's non-HDL and triglyceride values. So it's total cholesterol minus HDLC minus this adjustable factor when it's below 400. So this is what we're talking about, and the National Institute of Health decided to try this. But look at what you have to do here. Gold standard multiple least squares regression. The authors propose an LDLC estimation as total cholesterol over 0.948 minus HDL over 0.971 minus triglycerides over 8.56 plus triglycerides times the non-HDL, which would be the LDL cholesterol, over 2140 minus triglycerides square over 16,100 minus 944. And they did this, and this is root mean square error is what this is. Over the root mean square error, if the higher the higher it is, the worse it is. So this is 32, so that wasn't good. 25.7 lower root mean square error, and that makes it a little more accurate and a little bit unbiased, a little bit more unbiased. Mean absolute differences. Now we talked about MAD. There's a show on MAD, mean absolute differences, and the mean absolute differences are a little bit different from where we talk about the mean absolute differences. Means you take each value minus the mean, and you take the absolute value of that rather than squaring it. Normally square, you square it to get rid of the negative, but in this case you would just take the absolute value. But that's what they're talking about here. So the MAD here is 24.9. The MAD here is 56.4. That's a heck of a difference between the mean absolute deviation. So or mean absolute differences. So that's what we have here, and that's the issue whenever we go about that. So what I did was I took a look at the accuracy of this stuff. Now I did not go into the actual Excel spreadsheet and do this type of thing here. But that is, you could actually do it yourself if you want to. You could take those numbers I just gave you, and you could put them in for each one for LDL, triglycerides, HDL, and actually plug them into this formula here and see how it works. See if the LDL is going to be as good an estimation from that as the estimation from the actual Friedewald aspect. And that's the Friedewald formula, right? So that's what we're talking about. Now, a new better equation. Here's it comes on. Now this is interesting because I took a look at AACC and I said, "Gee, what's AACC?" And they, they don't say that anywhere in here. It's the American Association of Chemical. Um, it's basically the chemistry. It's basically the health labs, is what it is. Clinical chemistry, the American Association of Clinical Chemistry. So that's what that AACC stands for. Well, I took a look at this, and they're into it too. A new equation averages B quantification to assess low density lipoprotein concentrates outperformed two LDLC formulas in recent studies, showing promise as a more accurate way of predicting cardiovascular risk. Sampson LDLC equation also has no intellectual property restrictions. So that's what I mean, it's a new equation, and you can even go to the new equation if you want. And this gives you what's going on here in clinical chemistry. So I mean, this is what we have here, and you can see new Sampson low density lipoprotein equation better than Friedewald and Martin Hopkins. This one right here was Martin Hopkins. That's the one I just went over. So this is the one that says, hey, this is what you do here. So it was, this is it right here. Authors propose LD estimation of this. So that's the Martin Hopkins right here. So Sampson, oh no, I'm sorry, this is the Sampson equation. Sorry, this is the Sampson equation here, right? So all of a sudden, this is, get out of here. This is what this is. So it's, this is it right here. This is the equation we just went over. So that's it. So that's how to do the LDL. We'll get that a little bit better for you guys. Where is it? So there it is right here. So that's it. LDL equal total cholesterol over 0.948 minus HDL over 9.971 minus triglycerides over 856. All these things are right here. So I'm just gonna take this right here. Take this right here, like this, and I'm gonna copy. See if I can actually copy this. And what we'll do is we will attempt to take this and put this into the into this. Maybe does it work? Yeah, it does. Okay. So this is the equation. So what we're going to do is we're going to take the LDL and we're going to take HDL. I'm going to take triglycerides, and we're going to have total cholesterol. So that's what we have right here. So the HDL, let's say the HDL is, I don't know, let's make up something. So 60, right? Triglycerides are 100. And the total cholesterol, it turns out to be is 260. So how are we going to do this? Well, the LDL is going to be equal to the total cholesterol divided by 0.948, right? Minus the HDL, which is here, divided by 0.971. I think that's the way. Let's make sure. I don't want to mess you guys over here. So let's make sure that is correct. Yes, that's right. Okay. So, oh, what am I doing? Let's go back. There it is. -71 minus, and then total triglycerides. So triglycerides over 8.56 plus triglycerides times what they call the non-HDL. So whatever the non-HDL is, we're just going to make that a 0 at this point in time. 0 over 2140 minus triglycerides squared, which is this. Do squared over 16100, and then minus 9.44. Okay, so your LDL is going to be 191. What if we went back to the free? We went back to the Friedewald, and we said so that's going to be equal to HDL plus, oh, I'm sorry, total cholesterol, right? Minus HDL minus triglycerides over 5. That's 180. So you can see where this is quite a difference. It in actuality is larger. It's more than that done by Friedewald. So this is the Sampson, and this is Friedewald. So that's, I mean, what does that do? Basically, what happens is we're underestimating the LDL. And if you're underestimating the LDL, then what that does is that puts you on a higher risk category. 191 is going to be a higher risk category than 180. Even if, let's say, if the triglycerides, let's say the triglycerides were, let's say they were 80, right? I just lowered that to 80. One's 194, the other one's 184. So, I mean, all of a sudden, but lowering that actually made that higher, which is interesting. The, and I probably messed up probably messed up probably you know what I'm going to do? I'm going to go ahead and parenthetical this thing, so we don't have any problems with. Please excuse my dear Aunt Sally here. So we're going to just do this whole thing, just so I make sure that we're going to be okay. Yeah, we're still okay. So I mean, it's a situation where let's make sure. Let's do this. Boom. We're just. I mean, I'm just going to make sure that we don't mess up anything here from the standpoint of what they call sequence of calculations. Yeah. So it doesn't look like it is. So that's. I mean, that's going to be your issue. It's going to actually, both of them are going to go up. One of them's going to go up that area. The other one's going to go up the other area. So, and that's because the total cholesterol, folks, is 260. That's why you're seeing a rise in this. It's got to make up, that LDL is going to make up for that 260. That's still the total cholesterol. So this is the type of thing that when you go into formularies, when you get into these areas of formula and whatever else, you can get into a really, really interesting situation from the standpoint of being able to take these formulas and make them diagnostic in nature. Because right now, the diagnostic formula is 50 years old. It's 50 years old. So by that measure, what we're doing is we are taking statistical data, and we are culling it, and we are doing whatever we need to do with it. And as a result of that, we are making data based on, it's based on a formula that is outdated. It's based on a formula that's outdated. So the Sampson formula is what seems to be better. The Friedewald formula is that which is, it doesn't seem to be as good as. And that's where we have to sit back and figure out exactly what we're going to do with this information. Are we going to press and use the Sampson information, that, basically the formula that's better, so to speak, or are we going to stay with the Friedewald? And if we do that, what does that do to our statin drugs? What does that do to our diagnostics? What does that do to cardiology in general? And how does that all work? And that's something that we're going to have to take a look at in the long-term aspect of medical diagnoses and statistics and data, because data that is based on something that is outdated, is that data reliable? Is it repeatable? Yeah, I mean, it is repeatable because you're using the same formula, but is it reliable? Is it unbiased? Because remember, you're basing the VLDL on triglycerides over 5, except in this situation where the Sampson formula is doing it a little bit differently. Now, interestingly enough, if you go back to my original area, we talk about Samson. Um, we talked about LDL cholesterol here from the National Institutes of Health, and they were talking about the Friedewald being no way. But then they started to talk about the um, the other one, not Friedewald, not Samson, but the one that talks about that. So it was Martin Hopkins. So the Martin Hopkins was a graduated triglyceride. So it wasn't triglycerides over 5. It was based on the triglyceride level. It was, and that's where that triglyceride adjustable factor has to fall in play. So it was a Martin Hopkins, and it was an adjustable factor. It was an adjustable factor. So that's where the Samson formula seems to be better. I mean, based on my fantastic Excel skills. So that's basically what's going on there. And I wanted to point that out to you. And you can go ahead and repeat these repeat these areas. You can take a look at different things. I mean, you can see, if you take a look at the you can actually see the URLs here. I know they're very small, but you can see the URLs on the different areas we're talking about. So, academic.eovp.com, aacc.org, acc.org, and then the National Institute of Health right here. So I know it's awfully small for you. I'm just going to go ahead and make this URL available to you, so at least you have one of them, right? So we'll do that one, and then that'll come up. So you can take a look at that, and then you can take a look at the different areas. Samson, we'll do that one. I will put that on there because this seems to have the formula, which you guys can then take a look at and make sure that I didn't screw it up somewhere along the line. So I'm hoping that that's not the case, but hey, you can never tell. So I'm going to put that up there too. So this way you can roll it back, you can copy it, you can do whatever you want to do. Whew, man, that was one subject, folks. We're there. I am so happy that you were able to stick with me during this entire episode to see that evolution of that specific formula, because I think it's kind of important. And having heart disease forever, it seems, over 30 years, it's nice to be able to take a look at that and see that all this time I've been trying to figure the formulary out so it'd be better. So it's good that somebody is trying to figure this out to make it much more reliable and much more accurate. So that'll only help me and all the heart patients in the world at this point in time. So with that, I will say adios. Thank you for watching the data show, and please, tune in next time. We'll see if we can continue with this medical type diagnostic formula type thing and see if we could take a look at it from the data perspective. Hopefully this sees you in a healthy environment, and will always see you that way. Remember, always check the data. Have a great day.